Welcome to SIM-PAC Live, where the rubber meets the road. I'm your host, Geoff Matthews, and tonight's subject is green aluminium. Are we there yet? I interviewed Dr. Mark Dorreen, who is Group Leader, Electrochemical Processing Mineral Resources, CSIRO. Mark is a world-renowned expert in aluminium smelting and is a former director of the Light Metals Research Centre at the University of Auckland. Welcome, Mark.
Hi, Geoff. How are you?
Okay. Now, for the viewers out there, Mark and I, we're just sharing a joke as we're coming on screen. We've been old colleagues. We spent 5 years touring the world together. We've spoken at international conferences all over the world. We've written, co-authored a number of papers on aluminium smelting and decarbonisation together. We've been to, I was counting before, but at least 10 different smelters in 10 different countries together. Mark is probably one of the most widely travelled people in aluminium. There's only be a handful of old guys and consultants. There's been as many Western smelters as you, Mark, and you've been to China something like 35 times for smelting. So you're pretty much the most experienced person I've ever met, anyway. And so it was an ideal time and to start to have this conversation. Green aluminium. Are we there yet? And I bring this up because two people in the past week have come out and said that they have made green aluminium with the use of hydrogen. Now, let's talk about that, and let's celebrate our wins, but let's look at not minimise the steep learning curve and what lies ahead and the role that lies ahead. And also talk about what that actually means, and also some of the other green claims out there regarding aluminium. So first of all, we'll start with recycling. We'll do recycling first, and then we'll do primary aluminium smelting second. That's new aluminium smelting. Because the releases in the past week were from EGA in the Middle East and from Norsk Hydro, who said that they've had zero carbon aluminium. And it's obviously from remelt, from recycling. And yes, and I was actually surprised, Mark, that they couldn't have electrified that process and that they needed to use hydrogen. Can you explain why they've gone down that route?
Yeah, sure. I'll give it a go. But and first of all, thanks for the invite to talk about aluminium. I'm now working at CSIRO in Australia, so I've got a wider brief than just aluminium. But the aluminium industry is and aluminium as a material is very dear to me, having worked in it for a number of years. Recycling of aluminium is interesting. Aluminium's a material where it can be recycled, over and over again, and some companies use the catchphrase "infinitely recyclable." Something like 75% of the aluminium that's ever been made is still in use because it's so easy to recycle, and we like to recycle it because it only takes about 5% of the energy to recycle aluminium compared to making new primary aluminium. So that's the reason why we're so interested in recycling. And obviously, the recycling market is very large. It's pretty similar in terms of the total volumes per year recycled aluminium versus primary aluminium produced. So when companies talk about their green credentials and the CO2 footprint of the aluminium they're producing, yes, it's a little bit easier to make those claims for primary aluminium. Things like the Aluminium Stewardship Initiative have introduced a very robust methodology for doing the accreditation and determining what the carbon footprint is of primary aluminium. For recycled or secondary aluminium, that's maybe a little bit trickier, but certainly companies are interested in doing that for obvious reasons. And one of the things that we then need to think about in how the secondary aluminium market can change the way it operates is what can it do to get away from the traditional method of heating the remelt furnaces to melt the scrap aluminium and then recycle it. So that's normally been gas-fired burners into large remelt furnaces. And yes, of late there are some companies, and there's the announcements you're talking about, where we're now seeing hydrogen being investigated as a fuel source to run those furnaces for remelting the scrap metal. There's an obvious question, which is why don't they just electrify? Now, I'm by no means an expert on the way these furnaces work. All I can say is that that electrifying would have been an easy solution if it worked in this instance some time ago. So you can imagine that had that been an easy option, people would have put it in play. So there's obviously some technical reasons why it's not easy to have electrical heating in these large furnaces in the environment that's there, where we still need to have a flame that's heating the furnace roof that then radiates onto the scrap metal and melts it.
Right. And there's absolutely nothing wrong with using hydrogen as a fuel source for those sources. We're going to have to use it for steel, cement, glass, fertilizer production. That's where we've got to go for those high temp heat applications.
There are some challenges around the potential for hydrogen gas to be dissolved into liquid aluminium, and therefore when that metal is poured and solidified in the casting process, for there to be some tiny cavities or little holes where the hydrogen was, and if you didn't remelt that aluminium again in a downstream process, it could cause a problem. So there are some challenges. They can be overcome with smart processing, and that's not a new thing that we need to overcome either. That knowledge is already known.
Right. So in terms of the tonnage, though, the total tonnage of what's recycled every year and what we've just been announced, it's really just a fraction of a percent, and we've got a long way to go.
Yeah, that's right. And this is also true in the primary market. The amounts that are being claimed to be genuinely green, zero carbon footprint and this largely pertains to the energy that's used in the process of remelting. Yes, there's only a very small volume.
Yes. So, and let's just stay on recycling for a bit, because the market for scrap. I interviewed Nadine Bloxham from Alfed in the UK, and when I was looking at that, the UK actually export more scrap aluminium than they actually import virgin aluminium, and so they're very good at recycling and collecting and recycling it out there. Other countries around the world are not so good. So we all need to step up. But I mean, I've called aluminium the beautiful metal because it is recyclable and it only uses a fraction of a percent of energy to remelt it, and this infinite recyclability. So we need to really capture all of that aluminium, so that 65-70% or whatever it is that's still in use. We need a true circular economy. We need 100% going back in aluminium, because the quantity required, they're now saying that we will need as much aluminium to be made between now and 2050 as we've made in the last 125 years. So, we're going to double aluminium again, and that needs to be truly circular. It's probably one of the easiest things to collect and recycle, though, of anything. I mean, an aluminium can, but even in building materials, aluminium windows and things like that, framing and that, it's probably one of the easiest. And we should put, more effort into it now, because it's one of the easiest to do. It's one of the easiest to identify and to sort out and to even get consumer behaviour in terms of cans and scrap. So recycling, we've just done a little bit. These companies forged a pathway. We should celebrate that. We should give them a pat on the back, and we should encourage them to do more, and everyone else to do more, really.
Yes, we should. Look, you're right. The world needs more aluminium. It's an amazing material for its properties. It's quite simple that, and it's widely accepted that aluminium is a really vital part of decarbonising industrial systems, decarbonising energy systems, changing the way vehicles are manufactured. So look, it's really important. Any steps that companies make, yes, they absolutely should be applauded. What we need is more companies to forge a pathway, and then we need, even quicker than that, we need more companies to follow them and get on that same pathway.
Yes. So shared pathways as well, in terms of, the technology behind achieving this also needs to be shared. There's no point trying to lock it up and patent it. We're not going to get there by companies locking technology away for 20 years either. So sharing those pathways. So let's come to primary aluminium smelting, and I want to for the audience and for anyone who hasn't followed aluminium, there's some critical numbers, and it's kilos of CO2 per kilos of aluminium produced when primary, and roughly about 50%, a little bit less, 48% is of all of the primary aluminium is made from hydropower. And hydropower, of course, doesn't have you're not burning coal, you don't have the bad CO2. So that aluminium from hydropower still has about 4 kilos of CO2 per kilo of aluminium, correct?
Yes. Yeah, look, that's right. In the process, and it's based on, it's called the Hall-Héroult process. It's named after the two people who invented it, one in America and one in France in the late 1800s. That process is what is used worldwide, apart from a very, very small quantity of development production. So that process is used worldwide. The process uses carbon anodes, and in the smelting process, the oxygen is removed from the alumina. The oxygen combines with the carbon and makes carbon dioxide. So in that process, you actually get about 2 tons of carbon dioxide per ton of aluminium from the carbon anodes. And then from other areas in the production chain, you end up with a number that's somewhere just under 4 tons of CO2 per ton of aluminium. So yes, we're making aluminium, but we're actually making a lot more carbon dioxide. So it's less than 4 to 1 for the production where we are using carbon-free electricity. If we then step up to using gas-fired electricity, we double that number. We're about 8 tons of carbon dioxide per ton of aluminium. And if we step up to coal-fired electricity, we basically double it again. So we're now in the range of 14 to 18, say 16 tons of CO2 per ton of aluminium.
Right, and I recall we were at I was giving a speech in London, and you gave me a statistic or a sentence to use from, I think it was a professor in Norway, who said that aluminium smelters were actually producers of CO2. That byproduct was aluminium.
Yes, that's right. Yeah.
And if you look at how much CO2 is produced per kilo of aluminium, you've got to agree with them.
Yeah.
So yes. So and this is also why that recycling is really important, because once you make it, and just so you follow the carbon or the embedded carbon, once you've made it, that carbon intensity put into it at the start is locked in forever. If you can recycle it without using any more carbon, essentially the carbon's been produced, and you've got this material you can use infinitely recycle that doesn't produce carbon anymore. So over the long, very long lifetimes that you could be recycling that, yes, there's an argument that you could get away with the initial carbon, embedding carbon into it, because and look, I'm not. I think primary aluminium smelting, we'll get onto it in a minute, can do more. I'm just saying that there is an argument that does hold up, that once you produce it, it's locked in, and you don't have to produce it again and again to use the aluminium again and again.
Yes, that's right. Under the current accounting methods for embedded carbon, we allocate all of that carbon footprint to the first use of the aluminium. So effectively, on all of the subsequent recycle and reuses, we only add the footprint of the recycling process,
yes,
not a portion of the initial. So yeah, whether the carbon footprint when the aluminium was generated as virgin material is high or low, from the recycling onwards, it remains simply the input from the recycling process.
Yes. Okay. So coming back to primary, so we've got these levels of carbon. There's 4 kilos with hydropower, around 8 with gas, and around 14 to 18 with coal. And when the grid is starting to decarbonise, like we have here in Australia, then some of that will be coming down. It won't all be at 18. It'll start to mitigate down because the grid's coming down. Now, we look at it was EGA who did a PPA recently with solar farm, and are producing now that they can follow the chain from the solar power they get during the day into the aluminium, and therefore halve their CO2. So instead of using gas at 8, they can be producing at 4 from solar power. Now, I actually applaud that, and one of the reasons I applaud it is you're aware you were on a call. We had an ASI call, stewardship call, back in about 2019, and I got into an argument with somebody from Bahrain Aluminium. And I said you could go out and you could introduce renewables tomorrow. You could take a third of your production and put it in a solar power. And they were just saying, and they know that was impossible. They actually said, where would we put all the solar panels? We don't have enough space. It's like, it's the Middle East. And so to see a CEGA come out in 2023, just 4 years later, and say we've purchased this massive watt of power during the day from solar power, that's great to me. We actually need more of that. And that should be applauded too, I think.
Yeah, and look, I know that it's easy to look at the industry and to be critical and say, well, they need power 24 hours a day, 7 days a week. They can't stop. So therefore, the argument that you can apply is, well, using solar doesn't work because what about nighttime? But the fact is that any use of energy that is clean is better than none. If you can use for if it's a small portion of your production, if you can use for a certain number of hours a day, that's better than none.
And it will be cheaper because given the price of gas, is that there's an international price now. Their solar panels will be providing them electricity much cheaper than burning gas. Even though the gas is essentially, they've got their own. I know they've got their own gas-fired power station and they've got their own supply of gas, but they could be selling that gas elsewhere for more. I would imagine.
Yes, and if you if you think about the potential value for in the marketplace for green aluminium versus dirty aluminium, there's an emerging market with some premiums. So there's some reasons to go green because of that. But obviously, companies see the whether there's trade-offs or not. They obviously see the value in signing PPAs for mixed power sources that include some renewables, solar or wind or both. And I think Portland in Australia is another example that's done that when they've renegotiated energy contracts.
Yes. And look, so I see some of the hydropower smelters are starting to use wind and their own wind, and they can buffer that and use their hydro essentially as a battery. They can use the wind when it's blowing and use the hydro when it's not. It makes totally sense too because it means, again, bringing in that variable renewable at a cheaper rate. It makes sense of decarbonising. So now, China is held up as the bad boy of aluminium smelting. Now, essentially, so viewers who haven't followed aluminium smelting, it's generally followed the cheapest form of electricity, and usually the cheapest form of stranded electricity too. So there's the big smelters in Siberia, and the smelters here were established at the same time as the coal-fired power stations and the coal mines. That was that thing, except for Tasmania, it was hydro. In New Zealand, we had stranded hydro, which we connected. So then, in about probably the 90s, maybe the 2000s, production migrated to China, because it was suddenly the cheapest form of power could be. They could basically, and I think you've been to smelters, you can describe them, where they just built them right next to the coal mine. And basically the power station is across the road, and there's a cable across the road to the aluminium smelter.
Yes, and it also wasn't even necessarily migration of capacity to China. It was a lot of this was as economic development and standard of living increased in China, and the internal demand for aluminium in China increased. They satisfied that demand by building their own smelters and rapidly increasing their own aluminium industry and the scope of it. So yes, that growth by and large occurred in areas where there is plenty of available coal. So we're talking about sort of some of the northwest, Midwest and Far West provinces, where large gas coal-fired power stations smelters located nearby, and largely using a combination of imported bauxite processed in China and domestic bauxite processed to make the alumina in China, anodes produced in China, smelters close to the source of energy, and then the aluminium, most of it used for domestic consumption and some of it being exported. And I think that aluminium was one of the materials that was considered when the Belt and Road concept was developed for shipping from China across Central Asia into Europe.
So, but what you've also, been to China so many times, they are developing renewables faster than anybody else on the planet as well, and including some big hydro schemes. I know there were some big hydro schemes that they built and then suffered droughts, and there's been aluminium smelters built and then closed down. But generally, those burning the coal it's becoming. They're even migrating away from it. Sure, I know that. In fact, I look at it and think, we burnt our coal over 125 years of industrial revolution, and they sort of burnt their equivalent over 30. So they might have done it a lot quicker, but they were going to build their economy on, like we've built our economies on the back of coal, they're going to build theirs and then they're going to get rid of it.
Yes, and we have seen in the last few years being a little bit of a shift. So in the Chinese market, there is a cap on the capacity of aluminium smelting that's allowed to operate. So and what's actually happened in very recent times is some of the Chinese companies that are wanting to expand capacity are looking elsewhere, looking at places like Vietnam, Indonesia, Malaysia, to see if they can build new capacity there. But within China, yes, there has been some shifting of capacity. Some of this is driven by the desire to improve the problem of the pollution from the coal-fired power stations. So if you force an aluminium smelter to close, you effectively create a situation where you don't need the power station to be supplying it. So if you close an aluminium smelter that's using coal-fired electricity, and then you rebuild that smelter in another province, and the province of choice has been Yunnan, where there was a rapid expansion of hydropower capacity. So a number of smelters relocated or new smelters were constructed in the Yunnan province. But it introduced another problem, which is that because of that rapid expansion of hydropower, there's not huge lake storage capacity feeding it, so it's a little bit more. We've gone from an issue of how do we, having continuous coal to now having disrupted hydro capacity because of the seasonal issues. So we've shifted capacity, and then the smelters have. So rather than the smelter being forced to shut down at periods of the year because the pollution is too high when they're burning a lot of coal and generating a lot of energy in winter, we've now got seasons where there's not enough water, not enough rainfall, the dams are empty, and then the smelters have to close down because there's no power at all.
And is that because they actually never took the time to fill them up, or is that just design issue with that?
I'm not sure. I think it's just a design that they went so quickly, and look, they built capacity that matched the energy demand, and without thinking about the storage behind it.
Yeah. Okay. So let's look at two more things on primary aluminium. So if you're in if you're grid connected aluminium smelter like we've got here in Australia, and that grid is decarbonising, and there's more solar and wind coming in, we're getting rid of the coal, there's a bit of hydro in there, there's some interconnections going on to keep it going. How do you contribute to the decarbonisation of the grid? Because I know you and I, and there's no point hiding it, we've got on record saying that, aluminium smelters can do more, and they can actually modulate energy. They provide some frequency response services now, and yes, they can shed load for a bit, but shedding load for a bit is very disruptive to the aluminium making process. It's very disruptive to the pots and the heat balance of the pots, and it's disruptive to everything, including shortening their life. Now, we've all suggested that your name is one of the names on the original NPOT patents, heat exchanger patents, but which expire very shortly. But that technology heat exchanger technology can mean aluminium smelters can go up and down in production 20%, possibly even 30% in some cases, at the turn of a dial, and start to actually act as a real battery for the grid without doing disruption to the smelters. And
Yes.
And if they did that, it means that they could have PPAs for a lot more renewables and be taking it in, and then they could get their 14 down to closer to 8 or whatever it is. They could move it downwards by contracting more renewables and taking more renewables and just doing some simple energy modulation. And they've been loath to do it for whatever reason. My prediction is when the patents come off in 2025, we'll see some activity. But it's inevitable that if you've got variable energy in the grid and you've only got some batteries and everybody else is helping the grid, people are putting their electric vehicles on solar timers or smart timers and their houses on smart meters to be able to integrate with a grid that's got a lot of power during the day and not so much at night. The smelters just can't sit there and say, no, we're not going to change. There's no social license for them to do that. It's not, and I know that they're going in the UK, they're going to the EU and saying we're a critical metal, so we have a special case. We have a special case to pollute the earth. It's like, yeah, really, and so I'm. You and I have both predicted that in 20 years' time, all smelters will modulate energy. They just will have to. So they might as well start down that journey now.
Yeah, I mean, I think there's a couple of issues here. Yes, they will have to. The social license won't allow them to be bullies in the grid that they've been in the past. So they're going to have to respond to that. But I also think there's this issue of that the industry as a whole says that it's developed a pathway towards zero emissions or reduced emissions, and then there's some waypoints on that, and following 1.5 degree reductions or sustainable development scenario things. I guess what we need to be careful of is that there's a bit of an assumption from an outsider that perhaps the industry is just progressively going to work its way down that path. I think the danger is that the industry does nothing for a long time and then hopes that at some point they drop off.
Right.
And so I think we need to be, there's the potential for the industry to say, yep, we're working on it. But in the meantime, there's actually not a lot happening, and perhaps while there's not a lot happening, they hope that the grid has become decarbonised and then sort of, job done, and they didn't actually need to contribute anything along the way. So there's the potential for that. There's also the potential for they're putting all of their eggs in only one or two baskets and really hoping that those baskets do hatch.
Yeah. Yeah. How I see this is, here's an analogy for you. It's like your next door neighbour buying an electric vehicle and you claiming you've helped the neighbourhood reduce your CO2 emissions. Yes, technically the neighbourhood's gone down its CO2 emissions, but you didn't do anything.
Yeah,
that's the bit that I'm saying that, I'm for aluminium. I think it's a beautiful material, and I think it's important to our future going forward and important to carbonisation. But you've got to be also taking some of the heavy lifting, and that to me is energy modulation. Because everyone in their own lives are going to be doing energy modulation at some point, in some way, in our homes and everything. Everyone needs to participate. So, okay, we'll move off energy. We'll move off that before we get too involved. I get too heated about it. But and let's come to the 4 kilos. So, to get the 4 kilos, there's only 2 ways I've heard of. There's ELYSIS, which is completely doesn't use carbon anodes at all, and I'll let you talk about that. And then just the other day, somebody said, well, if we carbon capture, and we carbon capture from, they were suggesting carbon from biochar or waste product or something, taking it out and making the carbon anodes, then the carbon going back will have if you made biochar, you'd reduce 50%. So what I'm talking about here, for anyone not following me, is if we let vegetation fall on the ground and that rots on the ground, and this is trees and forests and whatever, it releases methane and it releases CO2. And if you burn it at a high temp pyrolysis, you only release 50% of the carbon that it does naturally. And then you use the biochar or black carbon or whatever they want to call it to make the anodes. You've reduced the natural carbon by 50%. You make the carbon, that goes back. And you actually had an even scorecard because it was going to be released into the atmosphere anyway. You've just delayed and used it. So you've offset some. Now, you said it's a quality of carbon that may actually be the issue there.
Yes. So there have been lots of attempts to use some forms of biochar, these reprocessing other materials to create a carbon material to use for anodes. So there's been lots of attempts, and so far none of those attempts have been successful. And the issue is it's to do with the microstructure of the carbon, and it's in the wrong form, so that if you make anodes and you use them in the smelting operation, those anodes, they don't have the right structural integrity, they perform very poorly, and by perform poorly, what I mean is they don't retain their structure, so we get a lot of carbon dusting, we get a higher energy consumption, so we effectively get more wasted energy. So we get a higher carbon footprint because we're using more energy to use these anodes. So they effectively they don't work very well in the process and cause a lot of disruption. So yeah, look, it's doesn't mean that somebody can't figure that one out, but they haven't figured it out yet.
Right. And so that's a challenge that could unleash something. Now, right. and that's taking something that would have naturally occurred, using the carbon, and then yes, you're releasing it, but you've made aluminium along the way.
Yes.
So where does the carbon come from now that you use in the carbon anodes?
So the carbon now is it's calcined petroleum coke. So petroleum coke that's been through a calcining process, and the petroleum coke it's a waste byproduct from oil refining. So it's a product that's generated when oil is refined. So yeah, look, I guess we can imagine that we do have some kind of really long-term problem if we imagine a world in the future where there is no more refining of crude oil, then we wouldn't have any coke from the delayed coking process to then make calcined petroleum coke to use to make anodes. But that's a lot further down the road. So right. Yes, it's a waste product or a waste byproduct from the oil refining industry.
Okay, now that brings us to ELYSIS. Which is not using carbon anodes. It's a technology that was developed by Alcoa and is it Alcoa alone or Alcoa and Rio?
Alcoa and Rio Tinto. So yes, what we're talking about with ELYSIS, but I mean we're actually talking about the concept of using an inert anode or a non-reactive anode. So rather than having a carbon anode that combines with the oxygen to make CO2, we have an anode that simply provides a surface where the oxygen ions get turned into oxygen gas and are liberated, and the anode remains intact and doesn't get consumed. So yes, ELYSIS are a very visible company. ELYSIS is a joint venture between Rio Tinto and Alcoa, with a large chunk of Canadian government money and a very small amount of money from Apple. So basically Alcoa and Rio Tinto combined their two independent and long-running developments in inert anodes, and now with some extra money working very hard to commercialise their version of an inert anode process. If we go back a couple of years, there was talk about that being perhaps being commercial ready about now, I guess.
Yes.
This year,
I remember. I was there.
So this year, I've seen comments from Rio Tinto in particular that they think that that the ELYSIS technology might not be really commercially deployed until perhaps 2030. And in fact, even just in the last couple of weeks, Rio Tinto have announced an expansion or a replacing of some old capacity at one of their Canadian smelters with some new capacity, and that new capacity is going to be using the AP60 technology, which is the newest and best Rio Tinto technology for using the conventional smelting process, and not the ELYSIS inert anode process.
Yes.
So within their own operations, they're not quite ready to deploy ELYSIS on a larger scale yet. Believe they've got it on a couple of test cells, and they're working very hard on that. And they're not the only company. Rusal have for a long time talked about this. It's a little bit of a mystery what's happening in China. We don't think there's any particularly strong developments in the inert anode field, but they could surprise us and something could pop up there. There's always potential for something to be done quietly in China.
So, and I remember that speech. I sat on a panel, and you were with me in Berlin when they announced that they were going to have ELYSIS up and running by now, and I think we looked at each other sideways back then. So so they have produced aluminium in their test cells, so haven't they?
Yes, they have, and this is where I think it was a very smart investment by Apple to be part of that process.
Yeah.
Because Apple have announced that they are using some of this, and if you use carbon-free energy in that process, there's no carbon involved in the anode. There's no anode reaction consuming carbon. Therefore, you do have carbon-free aluminium. So it's a great story for Apple to talk about having genuinely carbon-free aluminium in iPads or iPhones.
Yeah. Okay. So when we talk about on this show with the rubber meeting the road, there's a pure zero carbon green aluminium. There is primary aluminium. There's been a little bit, like maybe to make it a car or something. We're talking about
maybe by now. I'm not sure. Maybe a few thousand tons.
Okay, a few thousand tons. And how many million are we up to now in global production a year?
Oh, we're in 60 something million perhaps.
Right. So we're talking a tiny bit. So again, we've got to,
but it's a start.
It's a start. We've got to celebrate the wins, otherwise nobody will start. So well done to Rio and Alcar and ELYSIS. But to get that to be all of the world's production by 2050 is that means rebuilding every smelter in the world. And
which in all likelihood is not what's going to happen.
So is it possible to carbon capture because it's in a pot room, the oxygen's going onto the carbon anode and it's releasing CO2? Could you carbon capture?
Yes, you could. I mean, carbon capture certainly works better when there is an elevated CO2 concentration, and that's why it's of interest in places like steel mill, off gas. Yeah, in aluminium smelters, yes, it's a much concentrated version of CO2. I'm not sure how the carbon capture and sequestration process works in terms of the other contaminants or gases that would be present in there. So I can't talk about that. But yeah, there's potential for looking at it as a concentrated source.
Yes, because when we get down to the very end, the bits we can't mitigate any other way, we're going to have to carbon capture. That's what I've never been a fan of trying to extract it out of the atmosphere now with machines, because it's just, it's not where you would start. You start with decarbonising the big things, the electricity grid, and doing the things you can, and then the very last bit, well, if you can't do it another way, you're going to have to carbon capture it. And so it's possible, because in the pot rooms, generally there's a ducting system that takes all those toxic gases, poisonous gases, whatever you call them, unhealthy gases, so away anyway. So it's being concentrated. It's technically you could carbon capture it if you could work out how to separate the good from the bad or whatever.
Yes.
Yeah. Okay. That's good. So to sum up then, we've got some truly green recycled aluminium, and we just need to go full throttle on that. And if that means it's got to make hydrogen production to do it, let's go full throttle. The electricity side of it, as the grids decarbonise, the smelters have to do more to retain their social licence. They can't just piggyback on everybody else's efforts and claim they're the one who reduce the CO2 content of the neighbourhood if they're not contributing. And then we've got the process, which, yes, there's some shining light analysis. There's a possibility you could use carbon from another source, a captured source, but it hasn't been done yet. And then there's probably the last resort of carbon capture, which if you can't. But yeah.
Yeah, and I mean, if we also think about that whole value chain, there's also considerable work being done by a number of companies in the bauxite to alumina part of the value chain. So of course, it's well known the work that's happening around reducing the CO2 footprint of mining by using alternative energy sources and vehicles and automating processes to be more efficient. In the alumina. In the alumina refining stage of this, taking bauxite and turning it into alumina. Yes, there's lots of work to change the energy source at various stages of that process. So we're talking about electrifying some of the process heat. We're talking about using hydrogen instead of gas as a fuel and calcination processes. So there are other stages, I think quite potentially very, very good improvements that are happening in the steps of the process before we get to the aluminium smelter, so that across that entire value chain we can reduce the CO2 footprint as well, not just focusing on the smelter itself. Yeah.
Okay, Mark, look, thanks. It's a great chat. As always, with you and I, it's always stimulating to talk to you. Yes. Thank you very much. And we'll look forward to catching up with you sometime. You're down in Melbourne. I'm up here in Brisbane, so it's not too bad for two Kiwis.
Yeah, no problem at all. Very, very good to talk, Geoff. Always good to. This is the similar conversation that we've had many times, sitting on an airplane or in an airport somewhere like that, mulling over what the industry needs to do to pull its socks up and be part of the energy transition.
Yeah, wonderful. Thank you, Mark.
Thanks, Geoff. Bye.